So I've started the recording. Hope everyone's okay with that. And let me share my screen. Can you guys see the screen?
Yes.
Yeah.
Great. So last time we had talked about this thing called bias and variance. And so at the left, we had a case of high bias, where the data was having a curve, a quadratic shape, but the model only had a linear capability. So the capacity of the model was not enough to fit the data. So linear means you just have a feature and that's multiplied by another parameter, which would be a number. That was high bias. High variance was where we have these features, where we have x, which is linear, x squared, which is quadratic, and then x cubed, and then x to the power 4. So here the model had much more capacity than what the data required. And the middle was the case where we had a linear and quadratic term, and it modeled the data pretty well. So how do we figure out in a slightly more
You probably have to click it on the. I don't know if it's automatically on.
I can hear somebody my singing. So how do we figure out in an automated way the right capacity for the model given the data? So let's say you have the model on the right. So my question that I would request you to answer is, how do we take the model on the right and move it closer to the model in the middle, which is just right?
Force theta 3 and theta 4 to go to 0.
Right. So, as Senthil said, this theta 3 and theta 4, if we can force them to 0 or close to 0, then the model becomes similar to the one in the middle. So that is the key intuition, is that you take a model which has a higher capacity than the data, and in your procedure for building the right model in an automated way, you try and force these extra parameters either to 0 or to lower values. Does that intuition make sense?
Yeah.
Awesome. So that's the key idea, that if the model's capacity is less than the data, then it has difficulty fitting the data. If the model's capacity is more, then it overfits the data. So we can have a model which has more capacity than the data. And in the model building procedure, we can do things to reduce the capacity of the model. In this case, if we can find a way to make theta 3 and theta 4, as Santal said, equal to 0 or close to 0, then the last two parameters features, they lose their value, and the model on the right behaves like the model in the middle. So how do we do this for neural networks? So we will talk about 4 methods to do this. So this is the first one. So this is called regularization, and you'll hear the word L1 and L2 and explain what both of those are. In terms of regression models, you will hear rich regression and lasso. Those are just some other words for L1 and L2, rather L2 and L1. So what we're trying to do in machine learning most of the time and in deep learning is we have labeled data which says what the truth is, and we have predictions. And we have a model with some parameters. We want to find values of those parameters so that the difference between the truth, the actual, and the predicted is minimized. That's sort of the key task. So that distance between the actual and the predicted can be measured in various ways. And whatever way it's done, we call that the loss function. And what we want to do is we want to minimize that loss function and minimize the difference between the predicted and the actual. So when a model has too much capacity, it has too much power, then it can overfit the data. Like in this extreme right case, it's fitting every data point. So we want to balance that with this term, which is nothing but taking the square. In this case, we have these thetas 0 to theta 4. taking the square of each of them and adding them up. Theta 0 square plus theta 1 square plus theta 2 square plus theta 3 square plus theta 4 square. So essentially what we're saying is we're telling the model minimize the loss function. So try and fit all the points as well as you can. At the same time, also minimize all these parameters. These are two opposing forces. On one hand, we're saying fit the data as closely as you can. On the other hand, we're saying reduce the parameters of the model as much as you can and make the model as simple as you can. And since these are two opposing forces, you get to decide as the one creating these models, which force do you want to give more weight to? So this lambda is that constant which you control. So if you give lambda a very high value, then the optimization algorithm will try to minimize the number of features. Even if it doesn't have very good prediction. So the loss may go up, but it bring down the capacity of the model. If lambda is too low, let's say 0, then it just focuses on the loss function and tries to fit the data as close as possible. That's the key idea. Does that make sense? So we have two opposing forces. One says minimize the loss, should minimize the difference or the distance between the actual and the predicted. And while you're doing that, also make sure that you minimize the capacity of the model, make it as simple as you can, but not simpler. So that's the basic idea. Now, if you're taking a square of these weights, so the neural network will have weights, which we denote as W's. Essentially, you're taking a square of all of them and adding them up. This is called L2, or Frobenius norm. Now, you could instead decide not to square them, but just take the exact value of all the W's and add them up. So what do you think is the difference between taking the values of W's and adding them up and taking the squares of the W's and adding them up? If we just take the W's, that's called L1 regularization. What the optimization algorithm tries to do is it tries to reduce the values of those weights. And for many weights, it will bring them to 0. It tends to focus on.
To be positive, or they can also be negative?
So the absolute values. That's a very good point. So yeah, we're taking, for L1, we are taking some of the absolute values.
Okay. So they're always going to be positive, even if it's not squared.
Right. Thanks for mentioning that point. So
it will descend so more slowly. That's what it is then. Yeah.
Say that again.
It won't. It'll be a little more slower than squaring it.
Right, and it has a tendency to make the weights go to 0 in case of regression model especially, and make the weights more sparse.
But the square also will do the same thing. They'll try to make it to 0.
So the square tends to do is, it tends to focus on the largest values and tries to bring those down.
So then why not a higher order cube?
Yeah, even that's possible. These two are popular, but you can definitely look into higher orders.
Okay. And what lambda is what? A scalar number, huh?
The lambda is your hyperparameter. So that is under your control, where you decide how to balance between the loss function and the regularization part.
No, what is it? Where do we set it? Is it just
So
randomly?
Sorry?
Is it a number we give randomly?
Right. So when you create the model, when you give it the training data and stuff, and you feed it hyperparameters, one of the things that you provide is the value for lambda.
How would we know the number of parameters? We wouldn't know, no? Hyperparameters. How do we know there are 4 in a model versus 6?
For parameters?
Yeah.
So the number of parameters are essentially the W's. So each layer has a matrix of parameters with the dimensions equal to the number of neurons in the 2 layers.
Okay.
So that's the number of weights. Plus for each neuron, we also have a bias term. So based on that, we can add them up for all the layers, and we get the total number of parameters.
Okay. Now, why would lambda be anything other than 1?
So let's say you have selected a model with lots of neurons and lots of layers, which has much higher capacity than what the data requires. In that case, you can keep increasing the lambda to force the model to use fewer and fewer neurons, or at least give them less and less weightage. In that case, you can increase the lambda to higher values, higher than 1.
Okay. It's more for transfer learning, huh?
Sorry?
It's for the transfer learning thing.
So transfer learning would be where we take an existing model and we keep all the parameters of that model which it has learned, and we change, let's say, the top layer, the top view, and we use it for different data training after that. So that's what transfer learning is.
Okay.
Thanks for all the questions. So if we look at, so essentially the optimization algorithm gradient, so there are a couple of them. The one that we have discussed is gradient descent, which is we get the gradient at a point for the parameters, and we see if we increase the parameter a little bit, how much do we get as the gradient? And we subtract that from the current parameter value. So if increasing the parameter increases the loss function, then instead of increasing the parameter, we decrease the parameter. And same the opposite. So that's what we do in the equation here. When we calculate the weight at time t plus 1, we take the weight at time t and we subtract the gradient of the loss function with respect to the weight. And we multiply that by alpha, which is our learning rate, which is what you would decide, which basically says if alpha is big, then you take big steps. If alpha is small, then you take small steps. So these two would have been the standard gradient descent. Now the new term that gets added is minus lambda into W. So if you take the derivative of lambda by 2 W square, you basically get 2 lambda by 2 W, so 2's cancel out. You get lambda W. So this is the new equation for gradient descent. Now, if you just take the first and the third term together, then you get WT minus lambda WT. If you take W out, it's basically WT multiplied by 1 minus lambda. So if lambda is a small term, then you're essentially multiplying the W's by a term less than 1. And that's what they call weight decay. So you're pushing the weights to go lower at every iteration. So the general gist is that when we add the regularization term in the optimization algorithm, it's trying to minimize the loss function, and it is also trying to minimize the weight itself. So that's one way to do it. And we will look at the code on how it's implemented. Let's look at the other way. So this is what Senthil had mentioned, setting the weights to 0. That was the case of a regression model. This is a case of neural networks. So here, essentially what we do is we force certain neurons essentially to 0. So, and the way it's done is that during one optimization cycle, when you're feeding the data, you have the forward pass, where the data goes through the entire network and makes the prediction. And then you have the backward pass, where based on the difference between the predictions and the actual, the algorithm tries to change the weights. That's the forward propagation, backward propagation. So when you do the forward propagation and the backward propagation, in both those steps, the exact same set of nodes will be made to function as zeros, non-existent. And then when you run the next batch of forward pass and next pass, you will randomly take some other set of neurons and turn them to 0. And with those particular set of neurons set to 0, you do the forward pass and also the backward pass. So let me say that again. And just to refresh our memories, forward pass is when we take the input data, we start from the first layer, we multiply that data with the weights, add the biases, feed it to the second layer, multiplied by the weights, add the biases, feed it to the third layer, do the same again, and we reach the final layer, we get an output. That's the forward pass. The output is our prediction. We check how much the prediction varies from the actual label, the actual truth. And based on that difference, we go back and we change the weights. And this is backward propagation. So those are the two steps. So now, in the dropout method, what we do is, before the forward propagation, we will take few neurons randomly and turn them to 0. And then we'll do the forward propagation. And with the very same neurons being set to 0, we'll do the backward propagation. This is one iteration. In the second iteration, we will again randomly choose some neurons and set them to 0. And then we will do the forward pass or the forward propagation, and the very same set of neurons being turned to 0, we'll do the backward propagation. So what impact does that have on the model? So what happens is, if you had kept the entire network, certain neurons could have been giving a lot of high values throughout the network. And that often tends to cause overfitting when we are mainly depending on certain neurons, which you can think of certain features being given very high weights. When you're randomly removing certain neurons, the algorithm is forced to find other neurons where it can give them very high weights. So instead of some neurons getting very high weights, now it's more distributed. There are more and more neurons which have sort of medium weights instead of super high weights. So instead of the model having some features which are overfitting, we tend to ensure that none of the neurons get very high weight, and more of them get low to medium weights. So it's more distributed throughout the network. And that tends to have a more balanced network, and that reduces the overfitting.
Avneet?
Yeah.
So the thing is that you could do this randomly for various sets of things removed. So you get various outputs, right? You have a bigger neural network out of which you have worked out various subnetworks with weights. Then to say what your actual output should be, do you some sort of take an average of them? How do you get to decide which one of these sub-neural network is best, or what average of them is best? Do you have to do something more here, or is it rather obvious how to proceed?
That's a brilliant question, Shantanu. By the way, happy birthday.
Oh, thank you, sir. 19-20. Chalo.
So that's a very brilliant question. So exactly as Shantanu said, is every time we have a different network, subnetwork being trained, how does that have an impact on the final network? And when this technique was started, then the approach that I mentioned was giving problems. And in order to solve that, a small change was made where the activation that was coming out of a neuron. So let's say you have a neuron which had 10 neurons going into it. Because there were 10 neurons going into it, you had 10 inputs multiplied by weights going into it. And now let's say at random, you're dropping out 20%, so you're dropping out 2 of them. So now what's coming out, the value is smaller than what you would have expected. And that creates a bit of a problem. So what worked was, is to divide. So once you have an activation come out of that neuron, which had 10 neurons going into it and now has 8. So you have the activation, you divide that by 0.8. So that increases the activation by 20%. And now that you're sort of in every iteration, you are changing the weights of some of the neurons. Let's say there are 20% neurons which you didn't change in one iteration. And the next iteration, maybe you'll change most of them, but some other 20% you won't change. So if you do this, let's say 1,000 times, you'll end up changing the weights of all the neurons. The key impact is that you won't be giving too much weight to a few set of neurons. You'll be diversifying to other neurons. And there were approaches, as Shantanu mentioned, to sort of take averages and during the test time and do it that way. So those approaches were done. They were used. The more popular approach is to sort of do this during training time. And once the parameters have been trained, where in each iteration, 80% of the neurons get trained. In the next iteration, another 80% get trained and so on. But over 1,000 iterations, all of them will get trained. But because some of them will be missing every now and then, the optimization algorithm will end up spreading the weights, thus not creating some neurons, not making them too powerful, thus reducing the overfitting. That was a very good question. So does this general procedure make sense? We do forward pass and backward pass to one iteration of optimization. And in dropout, what we do is we randomly take some neurons, we set them to 0, we do the forward pass, backward pass. The next iteration, we randomly take some other neurons, set them to 0, do the forward and backward pass, and we do this, let's say you can do this 1,000 times, or whatever number you like. And that way the weights get distributed, and your model is more regularized. Does that make sense? Any questions?
Oh, that's quite nice. Yeah.
Okay. So these are the two main methods. There's one quick point about the previous method, which is, let me bring the sigmoid function. And let me bring the ReLU function. Okay, these are some modifications on ReLUs. We want good old-fashioned ReLU. Let's go to Wikipedia. Or how about this one? Okay, this is a good one. Yeah. So the regular ReLU has a straight line. Everything below 0 is pushed to 0. Everything higher than that is the same value as the input. And it's also a linear function. The sigmoid is more of a curve. Now, there are two interesting things about regularization and neural networks. One is that in regression, the L1 regression, where we take, as Senthil pointed out, the absolute values of each parameter, we sum them up, and we try to reduce them as part of the loss function. So in regular regression, it tends to bring them to 0. In neural networks, that hasn't been that powerful, or that it doesn't have that effect somehow. So neural networks, what's more popular most of the time, what people use, is the L2 version, which is take all the weights, square them up, and add them up. That is one point I wanted to share. Of course, you can play with both, see what works for your problem. Every problem is different, but that's the general rule. Second is, when we do the L2 regularization, then somehow whenever the weights are very high, so you would be on the upper right corner, L2 regularization forces them in the range closer to 0.5. It doesn't let, so when we initialize the weights at small values, somewhere around 0.5s, or somewhere between 0 and 1, random numbers. So the L2 regularization forces these weights to not go too high and sort of remain closer to their initial states. That makes it stay in this range, which is close to 0.5, where the function is fairly linear. Even though this is a sigmoid function, if we force the curve to be mainly active around the middle, it ends up acting as a linear function. That is what it turns out is the key thing that happens during L2 regularization. So in general, deep learning is optimization is a very complicated space. It can have hundreds of millions of parameters. So researchers are getting better and better intuition, but because such a high-dimensional space, there's still a lot that researchers are figuring out. This is one of the things that was observed, that an L2 regularization, so which end up having values between around 0.5. So the activation function acts as a linear function. Okay, back to our third strategy. Who doesn't like cats and dogs? So we had mentioned that we want our model's capacity to be similar to the complexity of the data. So if a model is too complex, we can use regularization to reduce the complexity and bring it closer to the data. Or we can increase the data so that it now fits the model better. Having more data sort of constrains what the model can do, makes it more difficult to overfit. Just like in the extreme right case, if we add a whole bunch of more points, right now we have 5, let's say we have 50, and the model tries to fit all of them, so imagine instead of 5 crosses here, you have 50 crosses. So even this very flexible model will end up behaving in a more smooth way. Does that make sense? So in the extreme right case, we have 5 data points, and the model curves and bends in multiple ways to fit those 5. But if there were 50, it wouldn't bend and curve as much. They would be all over the place. And the model would end up being more smooth, as long as it's this model with 5 parameters and 4 features. So the same idea is here. If you want to take a model which has a lot of capacity, which we call a high variance problem, the model has a lot of capacity to constrain it. We can give it more data. Problem is that labeled data is associated with a cost. So if you want more pictures to be labeled as cats and dogs, you have to hire people, you have to pay them money, and get the data labeled. What if you don't have funds for that, and you still want more data, more pictures? That's what this idea is. You essentially have methods. I think Keras has a bunch of augmentation methods for images, where you take the image and you rotate it in multiple ways. You can get its mirror image. You can rotate it left and right. You can zoom in. You can zoom out. You can crop the data, like in this one, and use those as your new data. Unhappy puppy. So that is the third method. And these three are the more popular methods. So first was L2 regularization, where we have the model try to reduce the weights in the neural network. The second, we take neurons, set them to 0, the activation functions coming out of them, and then do the optimization, which tries to ensure that some neurons don't end up getting too much weight. And the third is, if we don't have funds to get new data, we use some augmentation techniques on the data and we create new data. So for images, you can have mirror images of the same image. You can rotate them. You can blur them a little bit. You can zoom in, zoom out. You can crop them, and so on. For other kinds of features, let's say you have real numbers and you have 100 real numbers in a single data point. So you have 100 features. You can do things like you can take 3 data points and find their median or their average or their weighted average and create a new data point. There are multiple ways where you can generate synthetic data in order to make your model behave better and not overfit. These are the 3 key methods. The fourth is, which is not that popular, but we'll still touch the idea. So when we are running the optimization algorithm, then it's reducing the loss function. The loss function is the difference between the actual and the predicted. The optimization algorithm is changing the weights to minimize the difference between the actual and the predicted. Now, while that optimization is going on, we can look at the loss function on the training set and the dev set at the same time. As long as both are coming down, things are fine. But when the loss function on the training set keeps reducing and the loss function on the dev set starts moving up, that's when we know the model is overfitting. And we stop the optimization then and there. So again, the optimization algorithm just tweaking the parameters to minimize the loss function, which is the difference between the actual and the predicted. So as it's minimizing the loss function, we check the loss function on the validation set and the training set. As long as both are going down, everything is fine. But when the loss function on the validation set starts moving up, while the loss function on the training is going down, that's when overfitting has started. We can stop the optimization algorithm right then and there. That's called early stopping. Those are the 4 methods. Do we have any questions on these 4 methods? Okay. Let's go to our notebooks and actually run these and see what it looks like. So you are going to need, so in the Nerd Buddies folder, there's another folder called Regularization for today's class. In that, there's a file called data.mat. So I shared the Colab notebook with all of you. So when you go to that notebook, if you run the first 2 lines, first one says from Google Colab, import files. Second one says actually import the file. Then you can choose in my case, it's on the local folder. In your case, you can go to the Google Drive. I have it in downloads. So you're going to need this file. This has the data for today's model. So once you have that, then let's go beyond all the fun pictures. These are the basic functions that we're using. So we'll just run them. This is some test cases. And these are some settings and libraries. So this is what our data looks like. It's again 2-dimensional data. And which means we have 2 input features. On the right-hand side, they're colored red. On the left, they're colored blue. And our task is to build a model that can separate out the data points of the 2 colors. So here we build a model which has these layer dimensions. So X is our input matrix, which has 2 rows many columns. That's the first layer dimension. The second layer has 20 neurons. Third has 3 neurons. And then there's a final 1 neuron. So we have, so for linear layer where all the neurons are connected to each other, that's one layer between the input and 20. And then we have a ReLU function. Then we have another layer between 20 and 30. Then we have another ReLU function. Then we have another layer between 3 and 1. 3 layers. And then at 1, we have a sigmoid function. So generally, when the output is binary, we use sigmoid. If it has multiple categories, we use softmax. And in hidden layers, we use ReLU or we use tanh, generally. So let's run this. So here we give a training data and test data. And the loss function is at 0.13. So the accuracy we get on the test set is 0.91. Training set is much better. It's close to 0.95. Now let's see what this looks like. This is what the model has learned to be the decision boundary. This is the interesting part. It has a general boundary between the red and the blue. It also has created these islands where it found a point deep in the red, there's an island for blue, and in the blue region, there's an island for red. And again, you can see some pointy things coming out of the red. While a real model should be somewhat a reasonably straight line with a little bit of curve, diagonal, across the two classes. So this is a simple case where the model has too much capacity for the given problem in the data. So let's try and reduce that. So let's first try the L2 norm. So how many layers did we have? 3. So we have 3 matrices for those 3 layers. And each matrix has the dimension of rows and columns of the number of neurons on both sides of the layer. So we have W1, which is one matrix, W2, and W3. So now we're adding this cost. We are taking lambda, which is the hyperparameter that we decide. We multiply that by the sum of the squares. So NP is the NumPy library, and B dot square squares all the numbers in the matrix, and P dot sum adds them. So we square all the weights, we add them up, divide that by 2n, and we multiply that by lambda. This is the regularization cost. And our loss function was cross entropy, which is here. So A3 is the activation function coming out of the final neuron, where we had just one neuron at the end. That was our prediction. And Y is the actual 1 or 0 label, the truth. So we send that in the cross entropy function, get the cost, we get the regularization cost, and we add these two up. That's your new cost function with regularization.
So it's one lambda multiplied to all the W8s, huh?
Right. So within the brackets, we have all the weights that are squared and added up. Then it's multiplied by lambda.
Okay.
Okay. So we run this. We take some test case just to see how it's doing. And now the back propagation is the step where we essentially find the derivative of the loss function with respect to the weights. And because there are multiple layers, as we go deeper into the layers, calculate that, we use the chain rule. So we'll go through that at another point in time. But the key thing to keep in mind is that we use the derivatives. We use the chain rule to calculate the derivatives of the weights with respect to the loss function. So here, these are for the W's. So the first part is what we would have used anyways. The second part, lambda multiplied by W3 divided by M, is the new part, which we had seen earlier as the weight decay. So same thing happens with the next layer W's, and same thing happens with the other layer of W's. So dBs remain the same, we don't touch them, and theoretically, even those can be regularized, but since the biases are only one per neuron, so the total number of parameters are just the total number of neurons, while the weights are essentially in each layer multiplication of the number of neurons on both sides of the layer. So those are huge. So in practice, regularizing the biases does not have much of an impact. So we leave them the way they are. So essentially, we can see that the derivative of the weights with respect to the loss function now has a new component, which is essentially going to force the W's to become smaller. This is just some testing. So now let's run again. This is running 3,000 iterations. So 3,000 times it sees the entire data set. So 3,000 forward pass and 3,000 backward pass. So now the loss function is higher, but the formula of the loss function is different now. We're adding weights to the loss function. So it's a different loss function. In terms of accuracy, now the test is 0.93, train is 0.938. Before, it was 0.91 on test. So the accuracy has improved on the test data. Let's look at what the decision boundary looks like. This is what we would expect. More or less a straight line, some tiny curves. So this is a much better model. And essentially what we did was we used L2 regularization. So in the loss function, we added lambda multiplied by the sum of squares of the weights, known as Frobenius norm. And in the derivatives, which we calculate during backpropagation, there also we had added lambda multiplied by the weight, divided by 2m. So we can see this clearly helped. Let's look at dropout case. So the dropout case was where we randomly take some neurons, set them to 0. So what's the key parameter for L2 regularization? It's lambda, which decides how much strength we want to give to the regularization part. In case of dropout, the key parameter is the keep probability, or the probability that you would want to keep a certain neuron. So let's say you have 100 neurons in your architecture, and your keep probability is 0.5, and in each iteration of forward and backward, you will have 50 neurons. If your keep probability is, let's say, 0.8 or 0.9, then you would have 0.8, 80 neurons, 0.9, 90 neurons. That allows you to control how much or percentage of neurons you will allow to go to zero. The other thing is that in theory, you can turn the input, the first layer, where you're entering the input features. So in our case, we have two input features. So in theory, you can turn them also to zero. In practice, generally, those are not touched. The input features are kept as is. The other thing to notice that, so we had studied the VCG16 model, which won the ImageNet competition in 2014. So that, I think, had about 138 million parameters. And if I'm not wrong, it was trained on about 14 million pictures. Now, about 80% of those 138 million parameters came from just two layers that were densely connected to each other. Each neuron was connected to each neuron of the next layer. So just two neurons, two layers accounted for 80% of all the parameters, all the weights. So one thing that you can do is, instead of assigning the same key probability for the entire model, you can have different key probabilities for different layers. So let's see how we do this. So we had one layer here, and we essentially take the dimension of the activation functions, and we create some random numbers. We see which ones are lower than the key probability. So on average, if the key probability is 0.8, then about 80% of them will be lower. And those will be true, the rest will be false. Then we multiply the activations matrix with D1. And this was the part where Shantanu had pointed out. This is known as inverted dropout, where we now divide the activation by the key probability to increase their values by the same amount which they were decreased by turning the neurons to zero. So if 20% neurons were turned to zero, now by dividing it by 0.8, sort of increasing it by about 20%. So we do that to this layer. We do the exact same thing again. So we randomly select which neurons in this layer to be turned to zero. We turn them to zero. Then to account for the lost neurons, we increase the activations by the same amount by which the neurons were decreased. So this is inverted dropout. So as Shantanu guessed, there are multiple ways of doing dropout. This is the more popular one. Let's test it. Let's see how it works. Let's run it. Okay. So the loss function is lower in this case because we're not adding parameters to the loss function. And it's much smaller even than the first case because I guess, not sure why. I guess it must have done a good job. The accuracy in the test set is much better. And 0.95. Let's look at the decision boundary. So this is what the decision boundary looks like. It's more or less a straight line with a little bit of curve. This also performed reasonably well. So those are the, so those are the two cases of regularization which we saw. So today's class, the main focus was how do we find a model with a capacity that's appropriate to the given data and the given task in the data. So in this case, classification. So if we take a model that has much higher capacity, then there are at least 4 ways of reducing the capacity to get it to a point so that it's a good fit for the data and the problem at hand. First method was L2 regularization, where we take the loss function being optimized and we add lambda, which is a hyperparameter which we control, multiplied by the sum of the square of all the weights, divided by 2n, where m is the number of data points. The second was inverted dropout, where the hyperparameter is the keep probability, which is what percentage of neurons we keep in the model. So for a given forward and backward pass, you take a random set of neurons, the number of which is decided by the keep probability, and we turn those random set of neurons off, their activations off. We run the forward backward pass. Then again, next iteration, we take another set of random neurons, the number determined by 1 minus keep probability. We turn them off, we do forward backward pass, and we do the regularization. Third, if the model has too much capacity, we try to give it more data. If we don't have more data, we try and synthetically create more data. On images, we can create mirror image. We can turn them, twist them, zoom them, crop them. And fourth was early stopping, where we see how the loss function is decreasing for the training and the validation set. As long as it's increasing, it's okay. But once they start diverging, meaning training is going down, validation is going up, we stop. These are the 4 methods we studied. We looked at the formulas, and for 2 of them, we put them into code. We saw them in action, and they work. That was the class for today. Do we have any questions regarding this?
No,
Okay.
I think I would need one more revision.
Sorry, please say that again.
I said I need probably one more revision.
Got it.
So I'll try to do it on my own, but maybe if we can just summarize this when we start next time also, it'll help, I think.
Absolutely. I'll do that next time. And if I forget, please just tell me again. We'll definitely do that. I'll also send you some material.
For some reason, I'm not run this code on my side. Yeah, I'll try to figure that out later.
Sounds good. Awesome. Was this timing, did it work okay for you guys?
Yeah, it's more confusing for me. I have too much active participation around me. So, but it was quite good. I mean, that's fine. I think I liked the class, and I would also like to. I'm not thinking too much now. I'm thinking, so I want to talk to you.
Okay. That's
Okay.
awesome. And I enjoyed the active participation. Thank you, guys, and thank you for the insightful questions and comments. Have a wonderful Sunday. Take care.
Thanks, Avneet. Thanks, everyone.
Thanks.